guys, this is going to be the recording for Wednesday, March 10th, and this is our second to last phase change lesson. And so we will be wrapping this up tomorrow on Thursday. And so today there's a variety of activities, and our main focus is the fact, or shall I say the question, do all energy transfers make a phase change? Do all of them lead to a phase change? And then our second focus is going to be on something called molecular attraction. And so, first thing we're going to do is you're going to open up the simulation. And when you open it up, you're going to notice that we have our four substances like always, but there's going to be a attraction level listed under each. And that's going to be really important today. And I will talk a little bit more about that in a second. But first, we're going to just do a little intro. When you have the simulation open, you're going to see that we're going to select substance B. And we're going to transfer in as much energy as we can. So we're going to put it all the way to the top. And then we are going to see if I can transfer out energy without causing a phase change. So when this opens, it's taken forever. Now that the simulation finally opened itself up, you can see I have level B here, and I'm going to click play, and then I'm going to transfer in as much energy as I can. I'm also going to click on my kinetic energy toggle up here so I can watch, and then I'm going to add in as much energy. And you can see that the more energy I am adding, the more movement is happening with my molecules. And also I'm seeing a lot more energy, a lot more yellow. I'm going to keep adding. All the way to the top. And so what we talked about in class is how the state right now, we know that's a gas. We see the molecules are moving away from each other. They're moving fast. They're moving kind of all over the place. There's not really a flow or a general movement. It's kind of random and chaotic. So that's a gas. So you're going to take energy out slowly to see if you can take energy out without causing a phase change. And so we kind of talked about if there's phase changes now, we said no. And I'm going to go another, let's see, we'll do another like 100 degrees or so and see. And there's still no phase change. So we've gone down this much, we still have no change, and we're going to keep going. Still no phase change. Gonna keep going. And so at this point, you can see I've taken out almost half. And did we have a phase change? We're close, but not yet. And so we talked about how it's definitely possible for energy to transfer in and out without a phase change. It depends more on the amount. So if I just have a little bit, it's not going to make a big difference. But if I add a lot of energy in or out of a substance, that's when a phase change happens. And we only have three phases. And so there's a lot of temperatures and a lot of room for only three phase changes. So that's kind of the conversation we had. And then we watched this demonstration here, and it doesn't have sound, so I can show you it. Before we watched it, we made predictions because there are four liquids, and we're looking at evaporation. And we talked about how all liquids are similar They're made up the same, but obviously not all liquids are the same. And so we have four liquids here, and we made predictions before they evaporated on which would evaporate first and which would evaporate last. And then we watched, and then we saw if we were right or wrong. And this is kind of an intro to the second part of what I said today was about, and that's our molecular attraction. And so before you really know much about it, think about what that could mean in this scenario. And so obviously make sure you make your predictions before, and I'll pause here in a second once it loads so you can see your four choices. It's orange juice, water, rubbing alcohol, and then nail polish remover. If it ever wants to load. And here it goes. And another cool thing to look at is they show you the amounts at the top as we're going through, and then there's also a timestamp at the bottom, so you can see that a whole day has passed, and then we'll keep going, and then a whole nother day has passed. So this is not a short process. Alrighty. So we figured out that our orange juice obviously was last, and then we had our nail polish remover that was first. And so we kind of talked about why we think that was the case. So then fill in your chart. And then there was the important key concepts down here, which I included because we're talking about molecular attraction. And so we kind of learned that molecules are attracted to each other, and there's different levels of attraction. There's weak and high, and there's medium, and all different levels. And so we can see through this chart, molecules in substance A over here have a weaker attraction than these molecules in substance B. So we're going to kind of focus today, and we're going to use a simulation to figure out how these molecules are attracted and how that affects what happens with our phase change and our energy and all those things that we've been studying. And so before you move on to the simulation, though, you're going to explain what molecular attraction means to you in your own words, and you can use those pictures that I have up here and kind of your thoughts on some of the activities that we've already done. And then in the sim, if you have it closed, there's another link. You're going to make a prediction before you start. And this is what I was talking about earlier in class. I'm going to stop it, and then I'm going to reset it. But what I was talking about is that each substance down here will have an attraction level. So substance B is medium, substance A is high, substance C is low, and then substance D is very low. And you can see how the molecule arrangement in each of our substances changes based on what you click. And so based on that, you're going to look at some predictions. And so if we took substances B and C, and they're both in the gas phase and they have the same energy, which do you think will have more energy transferred out in order to make a liquid? Because remember, we have to transfer out energy to make a liquid. And depending on what the phase change is, you're either taking energy in or pushing it out. And remember that directly relates with temperature too. So if something is getting colder, we know that we're taking that energy and transferring it out. If something's getting warmer, we know we're taking that energy in and having it being transferred in. So you're going to make a prediction if substance B or C is going to need more energy transferred out. And then for the simulation, you're going to follow these instructions right here. So you are going to transfer energy in, and you're going to do this for both. And you're going to transfer energy in to B as much as you can, because remember, we have to have B and C both starting at the gas phase, which is the highest temperatures and the most movement. So you're going to try to get it, and you're going all the way to the top because it's really important that both of the substances start at the same level of energy and same temperature, because that will give us accurate results if they're both at the same. And if they're both different, those are not accurate results. So you go all the way to the top. And so you're going to figure out how much energy is needed. So you're going to slowly transfer the energy out, and then you're going to notice at what temperature it changes to liquid. And that's going to be like a roundabout guesstimate. You're not going to be able to tell me like exactly, just get as close as you can. So you're going to transfer energy out slowly and tell me at what temperature about, remember temperature's over here, that it becomes a liquid. And you're going to do that for both. And I'm just going to do it until I notice it's changing phase. And remember, the liquid will be mostly at the bottom, and they'll still be moving, but it's going to be more movement in place, and they all move together. So that the point where they stop kind of flying all over and bouncing off the walls here is what we're looking for. So I would say about and see, I'm playing around. I'm just kind of looking and observing. I would say more like 50-ish degrees. Maybe you could get away with like 60. And so you'll do that for both B and C, and then you're going to put the temperatures down here. You're going to do the same thing for test 2, but you're going to look at A and B, and now they're both solids, and you're going to see what's going to be needed to change them to a liquid. And so you'll do the same thing, but you're going to start with having the lowest amount of energy. So you'll minus all the way to the bottom, and then you'll add in energy to see when it goes from a solid to a liquid. And then there is a reading, and that's that.